this. This is solar site assessment. So we talked about the electromagnetic spectrum, flux density. The important thing to know about flux density is, let's see, 9 to 3 are the hours of collection that you're most concerned with. Anything before 9 o'clock in the morning or after 3 o'clock in the afternoon, the sunlight is going through a lot of atmosphere, and most of the usable energy is being reflected and refracted and absorbed, and it's not doing you very much good. So if you're shaded before 9 o'clock in the morning or after 3 o'clock in the afternoon, don't worry about it, because it's not going to hurt you that much. Yes, we were talking about the difference between ultraviolet and infrared radiation and how much difference does that really make. Ultraviolet is very short wavelength, very high intensity. One of the things about the electromagnetic spectrum, which I normally write up here on the board and show you where all the different things fall into it, but it's enough to know that the shorter the wavelength, the higher intensity you've got. So ultraviolet is much more powerful than infrared. Infrared is long wave, it's heat, but it doesn't have as much embodied energy as the shortwave ultraviolet does. However, making use of the shortwave ultraviolet is a little more difficult, which is why solar cells can't really use it. Solar hot water systems can't really use it. Passive solar does. Yeah, the more atmosphere you're going through, and this is another thing that I normally would talk about, is what happens to the energy when it comes down to the planet. And so without writing it all up on the board, I'm just going to say the solar constant is the amount of energy that hits the top of the atmosphere, and it's 429 BTUs per square foot per hour. That's a lot of energy per square foot. 429 BTUs per hour is hitting the top of the atmosphere. So that's a lot of energy. One of the things I think is also in your book, probably right up here toward the front, it says that the energy falling on Lake Mead is 5 times the amount of energy that the Hoover Dam produces in a day. Just the sunlight falling on the lake, the big reservoir that they produce when they put up the dam, 5 times what the dam produces. So all we need to do is figure out how to use it, right? Sounds simple. Plants do it. If we could figure out how photosynthesis actually works, we'd be there. We wouldn't need oil or coal or nuclear or gas. Why solar? That's about that far back in your book, so it's about halfway through, I think. Every day, enough heat falls on the paved roads in the U.S. to supply all our energy needs for that day. Solar energy falling on Lake Mead each day is 5 times what the hydroelectric dam produces. There's not a country in the world that uses more energy than the sun provides to the surfaces of the buildings within that country. So, you know, the only reason that we started off using wood was because it was easy. We knew how to do it. You could start a fire a lot of different ways. Then we moved to coal. Coal has slightly better embodied energy. It has a little less pollution than wood, believe it or not. When you have a wood stove, the best ones, 60% of the heat is going up the chimney. And you know, if you're lucky, you're not producing too many unburned hydrocarbons and all that stuff. If the stove burns hot, it can be sort of clean, but it's still not as clean as coal. And coal is not as clean as oil, and oil is not as clean as natural gas. So we keep moving up the food chain, so to speak, and getting more efficient as far as burning the stuff, and we're also getting more efficient as far as not producing a lot of pollutants. But you know, we're still turning stuff, and we can't keep doing it. And we haven't dropped off all the things that we've bypassed either. There's still people heating their houses with wood. You know, if you go out into Snoqualmie or out into the sticks somewhere, there's a lot of people that heat with wood because it's cheap and they got lots of trees, and you know, trees fall down and die, and it makes sense. But it's an incredibly polluting way to heat. And coal, you know, we're still, most of the energy in this country comes from coal. The atmosphere is blocking out almost evenly the whole spectrum. Because if you think about it, it's, I'll draw you a little picture right here. If you got a circle, and then you've got the atmosphere, which is a bigger circle, the distance between here and here might be x. So that's, you know, noon. That's when the sun is directly overhead. By the time the sun is setting, it's over here. And this number might be 2 times that x. So the more atmosphere you're going through, the more chance there is for the dust particles and the water vapor and the ozone and everything else to take that radiant energy and reflect it, refract it, absorb it. So of that 429 BTUs that hits the top, remind me again if I forget again, 35 to 40% is reflected back to space. So it's reflected back by dust, water vapor, in the clouds. Also sand, snow, and surface water on the planet. Part of the radiation that makes it through the atmosphere is scattered by dust, and that's why the sky is blue. It's called Rayleigh scattering. And what that means is that every color except blue is getting absorbed by the dust in the atmosphere. The blue is getting reflected to our eyes, and that's why it looks blue. It's an interesting fact that the reason that this looks yellow is because it's absorbing every color except yellow. It's reflecting the yellow light back to us, and that's why it looks yellow. But every other color is being absorbed. It's kind of a weird way to think about it, but that's, from a scientific standpoint, that's what's happening. 10 to 15% of the radiation that hits the atmosphere is getting absorbed. If it's getting by, it gets absorbed by water vapor, CO2, and ozone. And this is where we get problems. You know, if that water vapor is absorbing too much carbon dioxide, then it stays in the atmosphere, and then it acts like a big greenhouse. The sunlight passes through the carbon dioxide, it hits something on the planet, it turns to heat, and then the CO2 is stopping that heat from making it back out. It acts like a thermal barrier. So it's sort of like glass, you know. CO2 is sort of like glass. It's clear when you're looking at the visible light and the infrared and the ultraviolet. The whole spectrum can pretty much make it through that CO2, but the heat, once it's turned to infrared, that doesn't make it back out. So that's our problem. So we talked about flux density, how much energy is coming down at noon as opposed to other places. 9 to 3 are the angle or the hours that you're concerned with. There's actually, between noon and 4 o'clock, there's twice as much radiant energy coming down at noon as there is at 4 o'clock. That's amazing. And mostly it's because of how much atmosphere it's going through. True south, I'll give you that one again. True south is 18 degrees east of magnetic south. So if you're facing compass south, what's that? Yeah, it does. Yeah, it changes 15 minutes. In 1992, it was 20. It changes 15 degrees or 15 minutes every year. So every 15 years, it moves 1 more degree. So eventually, north is going to be south, and south is going to be north. And pilots know exactly what the declination is. So altitude angle is the number of degrees above the horizon that the sun is at. And on December 21st, it's at 20 degrees. On the equinoxes, it's at 42 degrees. And on the summer solstice, it's at 65 degrees. So to make it a little easier, if you want to do a site assessment, go out to where you think you want your panels, face true south, 18 degrees east of magnetic south. So if you're facing magnetic south, just shift yourself 18 degrees to your left, and that's true south. And then hold out your arms like you're going to give somebody a big hug. That's 9 o'clock, that's 3 o'clock. And then put one fist in front of you, the other fist on top, and that's 20 degrees. So that'll show you where the winter sun is. That's the lowest that the sun ever gets. 65 degrees is, way up here. And you can also use the Pathfinder, and I'll show you how this thing works. So that's altitude angle. Azimuth angle is how far off of true south the sun is rising and setting. And it changes with the seasons. In this page that looks like this one, you can see that in the wintertime, the sun is actually rising in the southeast, and it's setting in the southwest. And in the summertime, it's actually rising in the northeast, and it's setting in the northwest. You can actually get sun through north-facing windows in this high latitude. And you can also use a protractor. This is our sun path chart for 48 degrees north latitude for Seattle. And this will show you where the sun is. This is the altitude angle over here on the right axis, and the bottom here is the azimuth angle. And so you can find out exactly where the sun is going to be for any hour of the day, any day of the year by looking at this chart. There's also behind this are other charts. It talks about orientation. You can be 18 degrees east or 22 degrees west and lose less than 5%. And then right after that, this chart here shows exactly what the sun angle is for every hour of the day. So if you really want to get into it, I gave you all the information you need to be as specific and precise as you want to be. So yeah, so solar position, ALT is altitude, AZM is azimuth. Horizontal is how much energy in BTUs per square foot is hitting a horizontal surface during these hours of the day and these months of the year. So you can actually figure out how many BTUs you're getting. And then if you figure one pane of glass is letting 85% through, 2 panes of glass is letting more like 75% through, you can actually calculate how much heat you're getting into your house. And to do the energy trade-off calculation that the state used to require, you needed to do all this. But there's always a couple engineers in the room, and so they're just going, cool, I like this. Normal clear glass, a single pane will let 85% of the whole radiant spectrum through. Low E glass will block out 3 times as much of the shortwave ultraviolet as normal clear glass. Now, having said that, there are 2 types of low E glass. There's soft coat, which is 90% of the market, and it blocks out 25 or 27% of the UV, whereas clear glass will block out about 9%. However, there's a kind of glass called hard coat low E, and it will only block out about 10%. So it's about the same as clear glass, but you have to ask for it. And the way to ask for it is using what we call the solar heat gain coefficient. So for solar windows, SHGC, solar heat gain coefficient greater than or equal to 0.76. And then visible light greater than or equal to 0.8. So what this says is 76% of the radiant energy from the sun that's hitting that glass is actually going to be transmitted through it. But you want to make sure that this visible light number is still up around 80%. And so this is how you know if you're getting a good solar window or not. And if you specify hard coat low E glass from the manufacturer, they can get it for you. You just have to tell them SHGC greater than 0.76, visible light greater than 0.8. I'm going to check the labels when it shows up on the job site, because every piece of glass comes with a label on it from the NFRC, National Fenestration Rating Council. And you look at those numbers, and if they're wrong, send it back, because they will try and slide soft coat in on you, because that's most of the market. Canadian companies, it's not a lot, because most of the windows now, when you order them, they build them. They don't have a whole warehouse with windows sitting in it. So you just have to tell them that you want it. I'm guessing it'd be less than 5%. Like, one of the biggest challenges to passive solar around here is most of the views are east and west. And, you know, people want to be looking at the views. So they've got all this west-facing glass, and then they've got reflection off the lake, which can add to another 35%. So what I do on west-facing windows, it's called low E squared. So normal low E glass has, okay, here's the sun out here. Here's you, stick figure. So normal low E glass has a thin film of metal on the inside surface of the outside pane. That's low E glass. And what it does is this real thin film of metal will let visible light go right through it. So you can't even see it. But when that long wave thermal radiant energy sees that film of metal, it gets bounced back. So it stops the radiant transfer out through the glass. So if that were low E glass, now I'm not radiating to that building outside or the tree. So it really makes a big difference. However, on the south side, close the drapes. You know, it's nighttime. You're not getting any solar gain anyway. All you have to do is stop the line of sight between you and whatever's outside, and you've stopped the radiant transfer. So you don't need the low E. But, you know, low E makes it idiot-proof. It doesn't matter whether you're home. You don't have to close the drapes. You're never going to lose radiant energy out through the glass. But you're also not going to gain radiant energy during the day. So I prefer to educate people so they're not idiots, and then you don't have to make the house idiot-proof, right? This is not that complicated. If you stop the line of sight, you've stopped the radiant transfer. Low E squared also has a thin film of metal on the outside surface of the inside pane. And so this long wave infrared energy trying to make it into heat you up, 85% gets bounced right back out. So for west-facing windows, that's a good idea, especially if you have a lot of them. Now, there's one other thing that makes it a little more complicated. I mean, you could teach a half hour just on glass, and we're not going to do that. But one of the things that makes it more complicated is there are 2 types of low E coatings. There's called an evergreen coating, and there's a cardinal coating. And if you look at a window kind of sideways, you can see whether it's got kind of a green tint to it or sort of a reddish tint to it. And you don't want to mix those two. Because if you're standing looking at a house, and you're looking at the corner of that house, and one's evergreen and one's cardinal, they're going to look different. It's going to look kind of weird. So that's windows in a real small nutshell. So what I usually recommend is low E squared if there's a lot of west-facing glass, hard coat low E or clear glass for the south side, and then any kind of low E for the north and east. Low-E, hard coat or clear. Yeah, hard coat Low-E or no Low-E at all. And argon is always a good idea. They put argon in the airspace because argon doesn't tend to convect as much, and it doesn't transmit the heat to the glass as quickly. In most places, if you buy a whole house full of windows, they'll give you the argon. But this is one other thing about argon. Anytime you put a special gas in the air gap between the two pieces of glass, if it's going over a mountain range and then coming back down, it's pointless because there's a little bleeder tube in there to keep these things from exploding with pressure differences, and most of the gas bleeds out through the tube. So try and find windows that are made on your side of the mountains. The ideal way to have a greenhouse is to have it a couple steps below the finished floor space, have a good insulated roof, have solid end walls. You know, you might have a window or a vent or something for cross ventilation, but the only place where a window is going to gain more than it loses during the heating season is on the south wall, south vertical glass. Overhead glass is going to cook you in the summertime, and it's going to lose like crazy in the wintertime. So don't do it unless you're growing tropical plants and you don't mind building a solar people cooker. Because in the summertime, you can't vent that space fast enough to offset that gain. I was an expert witness for a builder. Well, it was actually for the homeowner who was suing the builder because they glassed 3 sides of this house in Anacortes. And you couldn't even sit in the living room, which was adjacent to the sunroom, because that common wall was radiating at 120 degrees. It was unbearable. And so they hired me to figure out how to fix it. You know, and they just thought, oh, we'll size some fans and we'll call it good. And I did the calculations, and you could turn that place into a wind tunnel, and it wouldn't get rid of the heat as fast as the sun can give it to you, because you're trying to fight radiation with convection, and it's no contest. Radiation is a third power transfer. It's like 1,000 times as efficient as conduction or convection. So the recommendation was insulate the roof, cover it up, make sure you don't get any sun in through the roof, put Low-E squared glass on that west side, get a decent overhang on the south side so you stop the sun from coming in the summertime, and then you should be okay. And I think we also specified Low-E paint. You can buy paint that will actually, you put it on that wall, and that wall will not suck radiant energy from you anymore. Yeah, it's kind of a wild thing. It's called radiance. And it does work. I did it on a common wall between a clinic and a garage over in Tonasket, where it gets really cold in the wintertime. And I just knew that that wall between the garage and the clinic was going to be cold, and these people are getting colon treatment, so they're all stripped down and getting tubes, and you know, you don't want to go there. But they're naked, so they didn't want to be radiating all this heat out to this common wall, and it worked. It wasn't cold in that room. I don't know. That's a good question. Environmental Home Center. That's a good guess. 682-7332. If you ever have a question about low toxic materials or recycled content, resource efficient, the Environmental Home Center is 4121 First Avenue South. It's just before you cross over the First Avenue Bridge. It's on the right-hand side back in one of those malls. Right, that is a railroad bridge. Yeah. So it's 41, yeah, it's in there, thank you. Yeah, it's a great place. It's a wonderful store. They know more about low toxic stuff than anybody else. So for trying to figure out what kind of solar site you've got, you can either do the basic solar site assessment where you stand there and hold out your arms and go like this, and you can get a pretty good idea how good a solar site you've got. Or you can get a solar pathfinder like Eric did. It's about a $200 item. And what it does is it's got this clear dome. So first you set it up on the little tripod, and the tripod's got legs that come out, and you can set it up on your roof. And set it up where you want your panels. It's got a little bubble level here in the center, so you can know that you've got the thing level. It's got a cradle here, so this thing slides for fine tuning. And it's got a compass, which is a really crappy compass, which is why I always bring my own. And you get it facing true south, and you've got this little sun path chart that looks pretty much like that one, except it's mirrored. And then you set the dome over it, and you put your face about 12 to 18 inches above it, and it mirrors the southern sky. So the best time to do this is on a cloudy day, because otherwise you've got the sun right there, and you've got to put your thumb over it so you're not blinding yourself. So it mirrors the southern sky, and then you take the grease pencil and you trace the trees and the buildings and any other shading that you've got at the site onto the sun path chart. And then the sun path chart shows you for every hour of the day, every month of the year. So this is the low winter sun. This is the high summer sun. These are the altitude angles up here. You can see 65 degrees at noon. The other way to find true south is compass works okay, but actually the most accurate way to do it is look in the newspaper. Find out when sunrise and sunset are, and go out to the site halfway in between those two moments and put a stick in the ground and look which way the shadow's pointing, because that's solar noon. Doesn't matter what the clock says, that's solar noon, and that shadow will be pointing true north. And that's the best way to find out true south. But so what this does is you've traced your obstructions on here. This is a big conifer tree, so normally I'd put a C here for coniferous. I would show branches if it was a deciduous tree. And you can see that this thing is blocking the sun in December and January from about, we're not concerned about before 9 o'clock, so we'll say from 9 o'clock until 10:30 in December and January. By the time you get up here into February, it's blocking from about 9:15 until, say, 10:15. So you're losing about an hour out of 6. And once you're up here into March and September, you're clear. So for a PV system, this is a great solar site. Because one of the interesting things about photovoltaics in this climate is that 50% of the output from a PV system in Seattle comes in June, July, and August. 3 months, we get 50% of the output for the whole year. 75% comes between the spring equinox and the fall equinox. So even if you're completely shaded for 6 months out of the year, you're only going to lose 25%. So if you've got some shading down here, this lower part of the graph, it's not that big a deal. I mean, for passive solar, I usually look at it. If they're shaded down here, I don't worry about it, because November, December, and January, you're not going to see the sun much anyway, and the days are so short. You're going to use auxiliary backup heating. There's no way around that. And in this climate, it's what it's going to be. February and October, these are getting into the swing months, where we do start to have some heating load, and if you're not seeing the sun, then you're losing. But March and September is when you really start to, you're going to miss it. If you're shaded in March and September, then you got a problem. And that's one of the other challenges too, is in March, you probably want the sun for heating your house, and in September, you probably don't. So this is where you get into user participation, because there's exactly as much radiant energy coming down on March 21st at 10 in the morning as there is on September 21st. So user participation comes into play. And you can set this thing up and you can figure out exactly how much energy you're getting on those panels and whether it's worthwhile or not. So this is worth doing. And I do site consults in the city. It's anywhere from $150 to $200, and I'll come out and spend 2 hours at the site and then write up a proposal for a PV or a hot water system. If you're just thinking about passive solar, I'll still do a flat fee site consult. What I usually do is best case and worst case. And normally, people run out of roof before they run out of budget, or they run out of budget before they run out of roof. 25 feet by 13 feet, that's a big area. I've also got an appraiser's report that came from the National Appraisers Institute that says a PV system will pay for itself dollar for dollar when you sell your house. It's one of the few things that will actually pay for itself again. So theoretically, if you buy a system today, you live in the house for 25 years and you sell the house, it will have paid for itself 3 times. So it's a smart thing to do.